Good morning, everybody. Thank you, Lucia and Matteo, first of all, for inviting me. It's a real pleasure.
Give me one more second
Okay.
to make sure that there's
So I will deviate a little bit on the topic now. Trying to present you some recent results that we had on organic polymers for different applications. So two applications that we had in mind. One concerns the realization of a gradient index material, controllable, tunable over a broadband. And the other one is the use of the same material for nonlinear applications. So the results, of course, are not have not been developed all by myself, but are the result actually of a very nice collaboration. With our electronics group in the Department of Information Engineering in Brescia. And for the nonlinear measurements, we have to thank Marcello Ferrera and, of course, Andrea Tognazzi from the University of Palermo and Dr. Scalora from USR. So let me give you a very brief introduction because I was not familiar with these materials up to 3 years ago, so I don't know if you're familiar with that or not. So we're talking about organic conducting polymers, which is a large class of high conjugated macromolecules. You see here a big table with lots of chemical formulas, different names. So whatever I'm telling you about, we're going to focus on P.PSS for our results, but whatever I'm telling you about P.PSS is also valid for all these materials that you see in this list. Now, the beauty of these materials is that they combine the flexibility and all the advantages of plastics with the ability to conduct electricity. So that's why we wanted to explore them. They're not new materials. They are widely used already commercially. So I'm not going to list here all the applications that involve those materials, but some of them, such as organic light-emitting diodes, are already on the market. So we're talking about something that has already a mature technology, and so that we are trying to see if we can make some good use in the optics community also for them. So if we let's start from the realization of the broadband tunable graded index medium. We are all aware of what is a graded index material. So it's a material whose refractive index changes with position. And actually, how they're usually done, the refractive index profile is set at the time of fabrication according to the application that you have in mind. So for an optical interconnection, we are going to have a certain profile, but if we want to use it for endoscopy, we need something different. So we wanted to understand if somehow we can make a device whose refractive index profile can be changed on the fly. There have been numerous demonstrations, and I'm sure that I'm not covering it all. Some of them use liquid crystals, some other have chemical control or acoustic control. Others use mechanical control, so they're actually squeezing materials so that you can make the refractive index change, also involving liquids. So they're all very, very nice. They have some limitation in terms of the the wavelength range they can cover. There's also a different kind of approach that goes at the nanoscale level. So if you are familiar with the metal surfaces, you know that you can achieve a very fine control over specific areas in a material, and you can create basically whatever refractive index profile you want, and you can actually control it through any of those mechanisms that you see here in this list. Now, what all these things, what is the main drawback of the metasurface approach is that you need a very, very good fabrication facility. And because we didn't have that in Brescia, we thought that maybe we will skip the fabrication part. So you see here some examples of very efficient metasurfaces that can perform beam steering or any kind of reconfigurable phase control by tuning the individual elements in the array. But as I said, we don't have any fabrication facility in our department. So we said, okay, we do that without doing nanofabrication. We wanted to have a high degree of spatial optical tunability, so we didn't want to compromise on the ability to set, for example, a radial control for a radial profile to start with, and then eventually change it. So we wanted to have complete freedom. Ideally, we wanted to also be biocompatible, flexible, you name it. So while still staying CMOS compatible, of course. So we chatted with our electronics friends, and they say, well, there's this class of material that actually we use for organic chemical transistors that might be good for what you need. So in particular, they work a lot with PDOT-PSS. So it's a combination of a conjugated polymer that is PDOT, that is what provides our conductivity, and PSS, which is a polyelectrolyte that balance charges and improves the solubility. Now, among all the properties that PDOT-PSS has, what we liked a lot was its transparency in the visible range. We want to make for example, an optical interconnection, so we need that to be transparent in a pretty broad range. But most importantly, we understood that we could modulate the refractive index properties, well, the conductivity to start with, and then the refractive index as a consequence, by injecting some ionic species from an adjacent electrolyte that stands close to PDOT. So if you take a look at how it looks like, it's like a matrix. It's our PDOT and the PSS on those big chips laying inside the PDOT. So it's a kind of mixed material. The tunability of PDOT has been proven in the microwave regime, but also in the visible and IR. And in particular, what has been shown is that you can tune a single element of PDOT or a layer of PDOT and change its refractive index properties to be from metallic to dielectric. Okay, so by applying an external voltage, you can change the refractive index by injecting or extracting those ion species from the adjacent electrolyte. And you see there's also some metasurface version of here. The nanoantennas are made actually of PDOT, and they are embedded into this between the electrolyte and an ITO electrode. So they will make a change the properties of PDOT and realize, for example, in this case, a beam steering device. There's another example here done with PANI, which is another organic conducting polymer that is also used for this purpose. But I said in the very beginning that we don't want to go through the nanofabrication step. Moreover, what all these tunable devices that I showed you do is to use PDOT-PSS as the dielectric filling capacitor. So they're changing the refractive index properties of PDOT in a bulk. They do not realize any refractive index profile. So we needed to resort to a different configuration. So when you sandwich PDOT-PSS between two electrodes, as they did before, what happens is that you start from a situation where you have no bias applied. So you have one electrode below and one electrode on top that is placed in the electrolyte. And you start with about 50% transmission in the visible range. And then you turn down, you apply a negative voltage. And if you look again in the visible IR, you see that your differential transmission goes up. And if you apply a negative positive voltage, you see your transmission that goes down. So basically your PDOT layer is turning lighter or darker depending on what you're doing. So in one case, you're injecting ions. In the other case, you're extracting ions. And what happens is that it changes color. But again, it changes color altogether. So we wanted to create a profile. So what we had to do was to apply a different connection configuration. And in particular, we resorted to what is called the OECT configuration. So the same that they use in organic electrochemical transistors. So instead of having just the PDOT, in this case is this organic mixed ionic electronic conductor, this OMIC that you see here in it's our channel of our transistor, is connected between the source and the drain. So if the sources and the drain are at the same voltage, you're back at the square zero, no? You're back at what we saw before. So if you have an equal voltage between these two connectors, what you do, you equally distribute the charge across the channel, and you change the refractive index properties in bulk. On the other end, if I apply a voltage drop between the source and the drain, I am able to create a charge distribution, as you do in a normal transistor channel, between the source and the drain. And so my charge distribution will then correspond to a different conductivity and therefore a different refractive index profile. So we made our device. This is a picture. It's not really pretty, but this is a sketch of the section. So in this case, we just use a sodium chloride solution because it was more practical for us to test and remove. But there's also another viable option with solid state electrolytes, so you don't have to worry about having liquids around. And this is our channel, which was 2 millimeters long. We measure the transmission first at equilibrium without voltage applied. We extracted the real and imaginary part of epsilon. And then what we did was to test, to evaluate, to apply voltage in different configuration, and to probe different regions of the channel to see how the transmission would change. And so we could infer how much the refractive index has changed. So we had a 2 millimeter channel, and our spot size was about 500 microns. So we had 4 discrete spots. And so what we found was that depending on so keeping the same relative voltage drop between the gate and the drain, so it's still 800 millivolts between the two electrodes, but adopting a different configuration, we could actually realize different transmission profiles, therefore corresponding to different permittivity profiles along the channel. So we probed from the source to the drain, and we saw that the transmission was going down. So in this particular configuration, where the two electrodes have equal and opposite voltage, you see that we actually can modulate transmission up to 60%. When you convert that, kind of extract the electric permittivity, real and imaginary part, you see that pretty much what the changes is the plasma frequency of the device, because the P dot can be modeled with a Drude oscillator and a set of Lorentzian oscillators, but actually the main change that we found was on the Drude part. So we are modulating the plasma frequency of about 40 nanometers along the channel. So the next question was, okay, well, what we can do with that, because this is not a metasurface, so we cannot control the refractive index at the nanoscale level, but still we can make some phase accumulation, because if I create the refractive index profile, I can accumulate some phase and create, for example, a lens. Okay, so we wanted to understand how much phase we could accumulate. So along between 600 and 1.6 microns, we tested several thicknesses and several voltage configuration, and we can see that pretty much depending on the electrode configuration and thickness, we could achieve pretty much the phase accumulation that we want. So, for example, if we imagine to put side by side in a sort of a ring arrangement, those two cells, what you do actually do is that you create a lens with a focal spot, whose focal spot can be controlled simply by changing the applied voltages. So if I take, for example, one of the 3 voltage configuration, and again, I'm thinking now just about a radial configuration, but you can arrange the electrodes as you want. They're not super tiny. They are kind of big in size. You can have a lens that can span a focus from 1 meter to 5 meters, so ranging from a telephoto to ground-based telescope, without actually touching anything, just changing the applied voltage on the electrons. And then because just for like personal deformation, we figured out that maybe because polymers generally have good nonlinearities, perhaps also these materials will have a good nonlinear response. So one thing that when we extracted the epsilon, one thing that we noticed was that the epsilon was rapidly approaching the zero as we went into the infrared range. And so we know that epsilon near zero materials, so materials that have their permittivity that goes to zero, have the main advantage of being able to, say, enhance the electric field for free. So it's just because of the continuity, the boundary condition at the interface makes your electric field go to infinity while the epsilon goes to zero. And this has been proven both theoretically and experimentally to be very effective for nonlinear application, such as harmonic generation. You see here some examples, but also for more extreme nonlinear optics. So they are ultra fast. You can achieve bistability in switching. You can create solitons. So all sort of things that can be done with regular good nonlinear materials can also be done, and probably even better, with ENZ materials. Now, one of the things that kind of happened over the years was that TCOs were appointed as the elected materials for this application, for these nonlinear applications, because TCOs have a very mature technology, and you can kind of have a certain degree of flexibility into tuning their properties when you fabricate them. So somehow you can choose where you place your ENZ condition according to your fabrication step. Now, when we looked at PWPSS and we noticed that also had ENZ crossing in the infrared range, we asked ourselves, how does it place? How does it compare with TCOs? And so what we looked at was this map that here you have the real part of the refractive index, here you have the imaginary part of the refractive index, and those blue, green, and yellow lines are our TCOs, so ITO, GZO, and ACO. And you see that PWPSS falls exactly in this region. So we say, well, let's see what happens with PWPSS. Now, of course, you have all things in life. You have pros and cons. So on one side, TCOs are very high conductivity, while those organic polymers, yes, they are conductive, but not as good. On the other hand, you can spin coat those organic polymers over very large areas. They are flexible, they don't break, they are biocompatible, so they have other advantages. So depending on the application, you might want to resort to one or the other. So we fabricated two different PWPSS layer, one in its pristine form, 170 nanometer thick, and the other one doped with ethylene glycol. The reason why we added ethylene glycol is because there are a number of papers that show that upon doping, actually the properties of PWPSS in terms of mobility, electrical mobility, change. And so we compare the transmittance, which is quite comparable between the two, and most importantly, we checked the real and imaginary part of epsilon, and we saw that we also have a different crossing for the real part of epsilon, that of course one at exactly 1500 and the other one at 1600. So we went ahead and tested the nonlinear properties in this frequency range. And so what we found, we measured, we did a near normal pump probe experiment. And we measured the transmission variation, so the differential transmission, as a function of the delay between the pump and the probe. And what we found was not only that, of course, we do have a modulation of transmission as expected. So we could quantify the nonlinearity of the material, but most importantly, when we switch from the pristine PDO to the dope ethylene glycol PWPSS, we have a dramatic reduction in the time response of the material. So we went back in the lab and measured the mobility and the carrier concentration. And we found that, yes, the mobility dramatically increases, but also the carrier concentration is different between the pristine P dot and ethylene glycol dot P dot PSS. So we attributed the change in time, which is like 7 times shorter, between the pristine and the doped P dot to this change in the mobility that is due to the extra doping. So we are currently planning to test it with even shorter pulse, right? Marcello is saying yes. But most importantly, we want to understand also if extra type of doping, different type of doping can also have an impact on the speed of this material. We model our system to quantify the nonlinearity. Now, because PDO-PSS is PDO-PSS and dope PDO-PSS, it's a very complicated compound. We have electrons, ions, polarons, bipolarons. We kind of summed up everything into an effective Chi3. And so what we found is that we actually have, over time, a refractive index modulation that impacts both the real and the imaginary part, but that is as big as 0.1 for the imaginary part and or the order of 10 to the minus 2 over the peak of on the overlap of the pump and the probe. So because at the very beginning we wanted to compare it with TCOs, we tried to sum up everything together. And what we found is actually that, yes, nonlinearity of those organic compounds is actually 2 orders of magnitude bigger. The time scale of the response is similar. I want to say that it's probably limited by our detection system or our pulse duration in this case. The mobility of the organic compounds is smaller, and the damage threshold is actually much lower. So on one side, we gain 2 orders of magnitude. On the other side, of course, we lose because organic compounds tend to break more easily. But it's still a very good nonlinear platform. So the way we see that is that these are not competitors of our TCOs, but rather more companions, especially because the organic conducting polymers are p-dope materials, while TCOs are n-dope materials. So we are trying to understand if the two things can be used together. So for the nonlinear part, I'm sorry the animations are all gone because I had to turn into a PDF, so that was supposed to be a more scrolling type. But for the nonlinear part, we tested the ultra-fast transmission modulation of these organic compounds, and found that they are quite good. There's still a lot to do at a very early stage. On the other side, we also have a platform for linear optics, which is very neat, in my opinion, and gives a very, very nice degree of freedom to play with, because you can really, without recurring to any nanofabrication, you can control the refractive index profile almost at will. Depending on the voltage applied and how you put together your electrodes. So with that, I would like to thank you for your attention. And if you have any question, I will be happy to answer.
Thank you for the very answer. I'm very curious. Have you tried to, or have you estimated how much you can change between the power of a green and slave with this effect?
Okay, so
The time scale and then
the time scale, okay, so we're pretty much limited. In this case was about 1 hertz. So it's kind of slow. But the ionic exchange is also slow. We do think that it can go a little bit faster, depending on the mechanism that is chosen. So the ionic exchange is not the only way you can, in this case, we had sodium chloride, so it was very kind of slow. With solid state electrodes might be a little bit quicker. I don't expect that to go into the gigahertz range, of course. But with different controls, maybe it can go a little bit faster. I would say probably in the kilohertz, but probably not faster than that. So it's I would say it might be good for yeah, I mean, if you have a telescope and you want to adjust it, you don't have that time issue. Of course, for real-time imaging, probably not.